All right, so it's recording now. Okay, share. I hope I don't mess it up this time. Okay, right, should be correct. Okay, so I have the Jupyter notebook. So today's topic is going to be the last topic, actually. So maybe that brings you some joy, right? That the torture ends, possibly. All right, so the last topic is we covered transformers already. As I said, I'm going to create a new video. Maybe take a look at that one. Correct the error I made in the last week. But the last topic is basically a continuation of GANs. So I've given you already how GANs work. Do you guys remember that? We went over the simple binary pattern GAN, which was this one, right? So you can refer back to that video, take a look at it. We went over the main concept, and this was a very simple GAN that created a binary pattern of 1010, I believe. Do you guys remember that one? Right. So today we're going to take this a step further, and we're going to look at a more advanced, more interesting one, which is going to be a GAN that generates numbers. So this is going to generate numbers like from MNIST, right? So handwritten digits, so a 7, a 3, a 5. But I'm going to also do conditional GAN. So I'm going to do the, because really I don't have time for both. And really the CGAN is just one addition to the other one. So I'll kind of just say, if you take this out, then it's, non-conditional. With this, it's conditional. And that should be enough. But it should be a lot of fun, because the idea now is it's like a generative AI, right? In the sense that in Stable Diffusion, you guys write, a dog in space wearing sunglasses and dressed as a knight from the Jedi Order, something like that, right? And it generates that image. So that's really sophisticated. And I'm not saying that I'm going to do that. But you could argue that I would say you can write the word 7 and it's going to generate a 7. You write a 3 and it generates a 3. One is, and that's actually very important. That's a conditional GAN. So basically a conditional GAN just means that we can actually tell the neural network what we want within what it can do. That's the limitation there, right? So this GAN can only generate handwritten digits, but it will be able to generate ones based on our input. All right. And so that's going to be our plan. Okay. All right. So I'm just as usual, I'm just going to copy the code from my GitHub, and that way it'll speed it up and I don't have to type it. At this point, all semester we've taken the same approach, right? Very object oriented, very much the same things. Okay. So let's go ahead and do that. I have it here. So you can as always, go to the PyTorch repo, then deep learning, then GANs, and then CGAN MNIST. That's the Jupyter notebook that I already have for this. So we're just going to run it. So I'm going to go ahead and run the libraries. All right, so we need to create, obviously, a new Jupyter. We're going to use the MNIST data, of course, for training. Okay. So I'm going to hit new Python 3. Okay. I'm going to rename this CGAN for conditional generative adversarial networks, MNIST. Okay. That should be enough. Name. I'm just going to say here. So CGAN MNIST. Markdown. Okay. All right, so let's add the libraries. So it's the same ones: Torch, NumPy, Matplotlib, and PIL image. Okay. Remember that we are dealing with images this time around, and we want to see them basically. A lot of this is exactly the same thing as the previous example. It's just a little bit more complex, but should be okay. Okay, so let's give it a minute. Okay, all right, so it loaded the libraries, no errors. Then let's go back here. All right, so this is a, I will go over this, but this is a class for loading the data set. I think we used it before for the MNIST CNN, so it should be familiar to you. All right, so let me just run it first. Okay, so this is basically a class, all right, so that we can do a lot of processing via an object-oriented approach. So it takes in the data set module from torch.utils.data. It's got basically these three functions in it. It's got this one len. It's got this one convert data to tensors, which I think we had covered this already. As I said, it's not the most efficient way of doing things, but it's very clear, I think. And then we've got the plot image function, okay? So let's take a look at plot image. So basically, it takes from the data set. Oh, yeah. One, it's a good question. What does, you mean this variable here? What is that? You mean this, you mean? I'm gonna go over this, so I'll explain it. Okay. It's a good question, and actually it's very important in this one because it's very relevant for us. All right, so, but let me just start with like the easy things. All right, so plot image just takes an index, right? And then it picks that from the data set, right? And it reshapes it because these are gonna be spaghettified, right? And we're gonna despaghettify them to 28 by 28. And then basically we're just gonna return the image so that we can print it. Does that make sense? So all it does is out of the data set, by index, we're gonna pick the image and label and have it available. All right, this is just should be very obvious. We're just printing the length of the data set. Now this is the constructor in it, right? So we give it the name of the file, which is gonna be the train set, right? And then we read it into data underscore df. We're gonna drop this axis 0. Okay, so it's probably the labels at the top. So I'd have to print it. So data frame drop label 0 axis 0. Yeah, I think it's the first row that's being dropped. Let me take a look actually. So I'll look at test set. Yeah, it's dropping the first the whole labels, all the labels. All right. Close that. All right, go back to the code. All right, so then we create these three lists: labels, tensor images, and one-hot classes, to kind of related to Lucas's question. So the list labels just has the labels 7, 3, 5, none, right? The tensor images list, well, it will be a list of the images as tensors, okay? And then this one will just be the equivalent label, but as a one-hot encoded vector. You see that, Lucas? So for instance, we have, this is going to be MNIST, so it's 10 digits, so it's 10 classes. So the vectors are going to be of size 10, where everything is a 0 except for the actual label. So if it's a 3, it's going to be what? 0, 0, 0, 1. That's what one-hot encoding means. Is representing the image as a vector. I don't want to switch to the whiteboard because this is what how I messed up this last time. So just to kind of answer Lucas's question, 7, right, Lucas? That's the label. The one-hot encoded version of it is, so there should be 10 here, 0, 0. 0, 0. 0. Okay, and then. Okay, so this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you guys see that? So the one-hot encoded version of this 7 would be 9, 8, 7. Like that. Does that make sense? Does that answer your question, Lucas? So it's just another representation. So both labels and one-hot encoded, one-hot classes contain the same information. It's just that one just contains the values as integers. The other one contains the equivalent vector representation. Got it? All right. Remember that dimension. And then here I just kind of hard-coded the number of samples for the train set, which is 60,000. All right, so that takes us to this function here, which is the data that the function that converts the data into tensors. So if you notice, it's going to do it 60,000. This is 60,000. So we read in all the data, right? All 60,000 samples into data df. So it's a 60,000 by 785 matrix, okay? Then we are going to grab the labels in the first column, right? So we're iterating in a for loop. So I grab the label, it goes in here. Let's say it's a 7, then a 3, then a 5. And then notice here what I'm doing. This is where I create this vector that I was talking about, okay? Very easily, I create a torch tensor of all zeros of size 10. Do you see that, guys? That's my one-hot encoded vector. And then all I have to do is I take target over here, and I just, by index, right, select the index that corresponds to this label, and that value gets assigned a 1. So that in the case of this 7, the index 7 would get a 1 there. And that's it. We one-hot encoded the vector, and we can use it now for deep learning. Any questions on that one? Okay. All right, so we do that. So we grab the label, we grab the one-hot encoded value, then we take from data frame, right? We take the corresponding index. Remember, you should be an expert in this by now, right? Right. So we're just slicing from not 0 is the label, so 1 is where the data starts until the end. We normalize it because it's easy to normalize MNIST. It's just divided by 255. And then we convert it into a float torch tensor. And that's your image now as a torch tensor of size 784, because that's how we get it from the CSV file. Okay, guys? Any questions? All right. So once we do that, then we just add these into the list, labels, tensor images, and so on. Okay? So that should be it. Any questions on this class for MNIST? All right, so let's move on to the next part. All right, so now we're going to read in the data set. This might take a little bit. We're going to instantiate the class with a name where the file should be. And it gives me an error. That's probably because it's in the same folder, isn't it? I think they're both in the same. Yeah, they're in the same folder. So let's just change the path. Okay, let's run it again. All right, it's running currently. Let's keep going. While it's doing that, we can discuss other code. All right, so once we have the data set, we can grab an image and a label. We've done a lot of this already. Okay, it finished, good. So I'm going to pick another image, let's say 173, okay? From MNIST data set, I'm going to invoke plot image. Okay, there we go, so I've got it. Now we're going to take a look at the data set itself, just so we can get a feel for it. And there it is. You can see it's mostly zeros because, you know, it's really only the data kind of in the middle that has values. The rest is just background. Okay. Then we're going to print out one of the numbers, the one we just read. So we're going to show it, and we want to see what the label is from the training data. So we run it. And what does that look like to you? A 5. A very odd looking 5, but a 5. You can see how this is what causes some of the variation in the training set, right? So that's a 5. Good. Now we're going to convert the data to torch format. So we're just going to invoke one of the functions in that class. So MNIST dataset convert data to tensors. So this is not the super, you know, it's kind of slow, but I just wanted it to be simple. All right, keep going. While it's doing that, we can print out the dimensions. You should always print out dimensions. Okay, we're going to need to give it a minute. And then we're going to need to create these functions. Okay. I can probably start describing what these functions do while it's processing. All right, so if you notice, I have several functions in here, right, that we're going to need. Call them like utility functions that we're going to need for the purposes of the GAN. We have generate random of a specific size, generate random image of a specific size, generate random seed of a specific size, and generate random one-hot encoded vector. So this is going to be generating basically the one-hot encoded vectors of size 10, but we're going to generate them randomly. Okay, so this is because the GAN, right? Whenever we're training a GAN, we need to give it something, right? Do you guys remember that we would give it something to the GAN? And it's usually a vector that is random, basically. So since this is going to be a conditional GAN, the trick is that we're going to give it the input to the generator plus the label that it should, the condition, basically. And that condition is also random. So you can see that here, this function basically will generate a vector of size 10 that is random. Then we're going to pick a number randomly from 0 to 10. And then that we use that as the index and we assign 1 to it. So it's the same thing we did before, only this time we're doing it randomly. So it's just like this part here, right? But this we did it according to the label. Instead, now we want to have a function that just generates that randomly. Okay, and that's because that's what we're going to use for the generative adversarial network as the condition. Any questions on this part? Okay. And then the other functions will just allow us to generate the vector for the input image. Okay, so we're going to have, you can see all of these are just invoking or creating tensors of a specific dimension with random values in them. Okay, so we'll come back to these as we start using them just to see what the purpose is. But for now, that's basically what they do. All right, so we finished this. I don't want to run it again. Let's just look at the dimensions. All right, so there's 60,000. And then let's just load these functions. Okay. So as I said, we'll come back to these, you know, and how we use them in once we need them. All right, so now let's move on. The discriminator architecture is very similar to what we had done before, and it's still pretty straightforward to use. Let's copy it. So the discriminator is that one, right? So we're going to go over here. Okay. Right, let me add. All right, so the discriminator class, what does the discriminator do in a GAN? It takes in the image and it tells you if it's real or fake, correct? That's basically its purpose, just like we described before. So this class inherits the NN module. It's made up of this function init, then the function forward, then the function train, and then the function plot progress, right? So if you remember, the plot progress function is just basically we keep a list of all the losses and then we plot it basically. So that should be pretty easy. Let's look at train. Train, notice that now train takes the input image, the target, but also takes the label tensor. Do you see how this is different now? This is the conditional vector. Remember that in a conditional GAN, you're giving it what you want, right? And to train it, you also need to provide that. Questions? Okay. This is a generative, well, this is the discriminator though. This is the discriminator, okay? So the discriminator will take in, guys, will take in the input, the label tensor, and the label, okay? So we'll come back to this one. Let's take a look at the architecture. This is the architecture of the discriminator, which should tell you everything about how this works, okay? If you notice, before, we would start with whatever the thing is that we're, let's say the painting, the Picasso, etc., right? We would read it in, and then we would output a neuron, either a 0 or a 1, right? So that's the label. That hasn't changed. It's exactly the same architecture. The hidden layers in between don't really matter, and this is basically MLP. Now, notice what's different here. This is new. Do you guys see that? 784 plus 10. What does that mean? It means the 784 is the image, and the plus 10 is the one-hot encoded vector. That's the condition. And astonishingly, just with this is going to start to work, right? But this is basically how we, if it was just a generic MNIST generator that randomly generates a 3, a 7, a 5, this would just be 784. But the fact that when we're training, we're providing the image and the corresponding label, that's what's really important. All right, so the information for the label will go there. So really the input is of size 794, not 784. Any questions? Yeah. Yeah, because we're going to give it the image and the vector, the label, the one-hot encoded vector. Why did I not code it as 794? Is that your question? Yeah, it's just to kind of remind you that it's the image plus the one-hot encoded vector. But really, I mean, it's 794, obviously. Yeah. Did I answer your question? Yeah. All right. Yeah, that's it. That's what makes it conditional here. All right. Then we've got the loss function, right, which is just a loss function for classification, like a cross entropy type. You can see binary cross entropy loss. The optimizer, the same thing, atom. This is where we keep track of the losses. So as you can see, that's basically it as far as the architecture of the discriminator. The forward function is really important because now this is where the magic happens, right? We provide the image, right, usually to predict the label. But now we have to provide the image and the condition that we want, right? So in this case, notice what happens. All we do is we invoke torch cat, which stands for concatenate. So we're basically concatenating the 784 plus the 10 to arrive at 794. You guys see that? That's it. All right, and then that becomes the input into the model, and the model will predict a 0 or a 1. All right, so we've covered the init function, we've covered the forward function, we've covered the progress function. So now let's go back to the train function, okay? So in the train function, we need to provide inputs, label tensor, and the targets, okay? So if you notice, forward takes the image and the label tensor now. So that's there, input and label. And that gives us the output, which is basically a 0 or a 1 for the class. Then we invoke the loss function where we take the predicted output and the targets basically that we are giving, just like we usually do. Does this make sense? Any questions? Okay. All right. And then that we calculate the losses, then we add them to the list. And then basically you should, no mystery there, right? We have our 0 grad, loss dot backward, and then optimizer dot step to update the weights. Any questions? So as you can see, the trick with conditional GANs is that we need to provide that label for it to know what's real, to map, the label 7 to the image that looks like a 7. Okay, that's on the discriminator side. Okay, I'll keep going. Okay. Now, let's take a look at running the discriminator. Control copy. Okay, so we instantiate the discriminator. So far, we haven't done anything with the GAN, right? We're just going to go over from MNIST data set, all 60,000 samples. We iterate one by one. We grab the label, we grab the image, and we grab the one-hot encoded vector. And now we provide the image, we provide the target, and we provide that this should be a 1, right? Because that's a real, we're training the discriminator, right? So we're telling it that that's a real thing. For a fake thing, we generate a random one-hot encoded vector. We also generate a random image, 784. So this is why we had these random functions over here. Okay, we want to generate a random image. So that's basically a vector of size 784. And then we tell it that this is class 0. Right, why? Because we're letting the discriminator know that that's what? A fake image. Is this clear, guys? Should be clear, right? All right, so fake image, fake vector, that's a fake. Real image, real vector, that's real. Okay, so we're going to train the discriminator. We're not training the GAN yet. I'm just showing training of the discriminator to get some intuition going. So let's let it train for a little bit. That will take a while. Then we're going to print the plots, or the plot, sorry. Here. Now we can run the discriminator on some data just to see how effective it is, okay? Copy this. Okay, so I'll describe this because it's still training. So basically here, we're going to do 4 examples from the data set. So notice that from MNIST data set, I'm grabbing an image and a one-hot encoded vector. You guys see that? And then I'm going to invoke d.forward, where I provide the image and the corresponding correct one-hot encoded label. And then that would predict either a 0 or a 1. So here, if it trained correctly, this should predict what? 1s, correct? Closer to 1, saying that they are true images. Then over here, I'm going to do 4 random images. So that's random image. That's a random vector. And the discriminator should say that those do not look like 7s or 8s because they're random data. Okay? Got it, guys? All right. So that's basically what we need to do. So it's training. That'll take a little bit, it seems. So let's keep going. All right, so we are ready to start describing the generator, okay? So let's describe the generator for our conditional GAN, our conditional MNIST GAN. Okay, so I grab it. Okay, so this is the class for the generator. Once again, it inherits NN module. the class is made up of these four functions: init, okay, forward, okay, train, okay, plot, and plot images. So that's just because I want to show some examples of images, basically, that were generated, okay? Plot progress just prints the losses. I actually think that I didn't use this function in the code, so I'll describe, I do this separately in another cell. So I'm actually not using this function. So I'm not 100% sure that it's totally correct. Just use the other one instead, okay? Because I remember I didn't use this one. All right, so we can ignore it. So I'll say here, ignore this function. Okay. All right, so plot progress we've described already, just prints the losses. Let's look at the architecture because that's usually what helps to understand everything. So if we look, this is the architecture, okay? So remember that GANs, their output needs to be what? The image, right? The thing that we're generating. So here, it's generating vectors of size 784 that we're going to need to unspaghettify later, right? And then we have some architecture, but now look at the input. It's interesting, right? If you remember, in the binary classifier that we use, our input was of size 1. It was just one neuron, and the value was like 0.50, if you remember. Here, the input to this GAN is 100. It's just a vector of size 100, but it's a random vector. Remember that GANs, as input, take in randomness and produce out of randomness something. And the example I kind of gave you is like in a TV, you had that snow thing back in the analog days of TV. Although that's not a good analogy, but it, it's just to give you something. There's got to be an input to the GAN, and it's usually a random vector or a random input. Why 100? I mean, it seems to be, enough information for it to discern an image. But you can play with that, just like maybe add more, add a little less, etc. Now, notice the key thing here, once again, is 100 plus 10. You see that? Because it's a conditional GAN. So this is actually really important. This 10 is the vector that represents the label from, 1, 2, 3, 4, 5, 7. So when this is a conditional GAN, we needed to learn that whenever we give it a vector and it's 6, then it should generate an image that's a 6. If we say that this 10 vector here is a 4, then it should generate a 4, and so on. Do you guys see that? That's what makes it conditional. If we didn't have this, we could just give it a random value, like 100, then it would just be a regular GAN. But then it would just generate 7s or 3s or 5s random. You see that? The fact that I'm adding this vector of size 10 is what allows me to actually get the image I want. Questions about that? This is the most critical part, I would say. Go ahead. Okay, I see what you're saying. So you have a signal and you're tacking on some information to use. Well, a signal is made up of, you can take a signal and decompose it into frequencies and things like that, right? Like a Fourier transform. So it's not exactly that. This is just concatenated at the end. So a better analogy might be that you have a signal and then you put more signal at the end of it. And then you just have to know, you get this part is the actual signal and then some additional thing. Yeah. So you have 100 and then plus 10, right? So that's the architecture, basically. Yeah. Yeah, go ahead. No, the 100 is not, the image has to be 784. Remember, it's 28 by 28, 784. This vector of size 100 is just a vector with noise in it. I know it's I know it's maybe difficult to like understand why, but that's how they work. Because one thing we know about neural networks is they always have an input and an output, right? We got to give it something. Think of it almost as we don't know what to give it, but let's just give it a vector with random data. Because remember that it's learning to generate from thanks to the discriminator. It's trying to fool the discriminator. So it produces an image and the discriminator will say it's fake. So what is it going to do? It's going to update the weights so that it can generate another image that's better and eventually fool it. Remember, go back to the binary example that we talked about. So this is fake. This is a 100 vector of size 100 with random data in it, and that's the input. Now this one, on the other hand, is not random data. It's the one-hot encoded vector. That's what makes a GAN a CGAN, a conditional, so that you can tell it, I want a 3, I want a 5. So this is always the label you want. This is random data. Okay, got it? Any other questions? All right. It's still going, still training, but it's making good progress. All right, so let's keep describing. So I talked about the architecture. Remember, you give it a random vector of size 100 for this example, and then your label as a one-hot encoded vector, and it should produce images of size 784. Then Atom, same thing. We save the losses, so that's pretty much the whole function of the constructor. The forward function is really important here, okay? So what does it look like? We give it the seed tensor. Notice that it just says a seed tensor because it's really just random data. But it's important that it's of size 100. This is of size 10. Very good. And then notice our very nice torch.cat, which means concatenate. What are we doing? We're concatenating this vector of size 100 and this vector of size 10. So in all, the input is of size 110. But this kind of goes back to Lucas's question. I don't do 110, or people don't usually do 110 to remind themselves of the fact that there's the 100 and the 10. Questions? Yeah. All right. So we give it this, we concatenate them, and then that's the input into the GAN to produce a 784 vector of an image. Got it? All right. So we've talked about the init function, and we've talked about the forward, and we've talked about these. So now let's just talk about the train function, okay? The train function for the GAN, remember, this is very similar to how we did this before, right? Remember that the GAN learns thanks to the discriminator, to the loss function of the discriminator, right? When we provide the inputs to the GAN, which is the random noise, we provide the label tensor, which is the condition, right? Vector of 10. And then we provide the targets. This is what actually says this is true or false, right? The actual label. Got it, guys? Okay, that's the actual label. So in this example, we invoke forward and give it inputs and label tensor, right? It's going to concatenate those two. And what does it produce here in G output? Our image of size 784. That image then, G output, becomes the input to our discriminator dot forward. Remember, discriminator will give a class given this. So in the training, we need to give it label tensor. Okay? Sometimes we give it a 1, sometimes we give it a 0. Remember, for the discriminator, that's a 0. For the generator, that is a 1. Remember, we can see that later. All right, so that produces the discriminator output. And then we invoke the loss function of the discriminator, right? D output and the targets. And that's basically our loss for the GAN. And then we just save the losses. And then once again here, we have the code that helps us to calculate the gradients and update the weights. Any questions? This is exactly as it was for the binary training function, okay? All right, so it's still going. Let's see how many does it have to do. All right, so it's at 800. It needs to get to 1200. Yeah. All right, so that's the generator class. So let's move on to the next segment of code. All right, so that's the generator. This would be, we haven't yet trained the generator, right? So what we want to do initially is, let's just run the generator with random data for weights, and let's see what it does. So it should produce an image of size 784, right? So I'm going to do this. So you instantiate the generator. You call forward. Remember, that's the function that we call whenever we want to generate an image. We provide generate random seed of size 100. That's the random vector of size 100. And currently, we can also give it a random one-hot encoded of size 10 with just random values. Just to see what it does. Whatever output is, we detach it from the computational graph, we convert it to NumPy, and we reshape it to 28 by 28. And that becomes IMG, and then we just plot it. So that's going to give us an image, basically. So only it's a random image. Okay, it's going to be a random image once we run it. Okay. So it should look like this. We'll see it in a second. And then now comes the sort of the magical part where we actually train the GAN. Remember that the GAN is made up of two neural networks, the discriminator and the generator. So I'm going to copy these two objects here. Okay, we would instantiate both. And then we do this part, and this is really where we actually train the whole GAN. Okay, so that's the code. I don't want to jump into this code just yet. I kind of wanted to finish training and describe this part. So let me see how close we are. It's at 900, so it's going slow. Oh, at 10,000 there. Okay. All right, so I guess we're going to have to describe this because we might run out of time. So this is the part, again, this is very similar to the binary classifier, almost exactly the same. But this is where we actually train both the generator and the discriminator together, right, to create this GAN architecture. So we're going to do 12 epochs, and we're going to iterate. So this, out of 60,000 examples, right, we grab each. So we're not doing it in batches. We're just doing it in batches of one, I guess. We grab the labels, we grab the images, we grab the one-hot encoded vector, right? So we grab them. We're going to train. Remember that we do 3 trainings. We do this one. That's one training. Then we do a second training, which is that one. And then we do the third training, which is this one, okay? So we train the discriminator twice and then the generator. Got it? So let's take a look at this first part. We train the discriminator on true examples. So this is probably the simplest thing to understand. We grab the image, the correct image, the correct label tensor, and we give it a 1. What does that mean? We're training the discriminator to know this is a real image. Got it? Then we generate a random one-hot encoded vector of size 10. That's for the next part, right? We're going to now train the discriminator on false data. So what do? We call G-forward, the generator, and we give it a vector of size 100, which is random data, plus this random label, which is the other vector of size 10, also with random data. It'll concatenate both to become a vector of size 110. Do you guys see that? So we invoke generator, that's a fake image, right, from the generator, and we give it to the discriminator to train on. But we need to tell it that the label is 0 here, right? Because we want the discriminator to know that that's a fake image. Do you see that? Does that make sense, guys? Okay. And the same random label, we pass it to the discriminator as well, because we also need it there, if you remember, right? So in the discriminator, detrain, let's go to the discriminator. That's the discriminator. In train, notice we gave it the input, the label tensor, and the target. So we need to pass that in because the forward for the discriminator needs the input and the label tensor. Okay? All right, so now here, this trains the discriminator on to predict 0 for fake images. But then we've got the last part, which is to train the generator, right? We want to train now the generator with a different objective, to fool the discriminator. So what do we do here? We create a random vector of size 10. We generate a random vector of size 100. So, and we also need to pass the discriminator. Remember that the generator trains with the discriminator, right? So we pass D, we pass the vector of size 100, which is random. We pass the vector of size 10, which is random. But the label we pass needs to be a 1, right? Because we want the discriminator to think that this is true. So this is why we pass this 1 over here. So this is going to do the G train. So if we look at G train, this is the generator. And so it needs to learn in the loss function that that's a 1, right, instead. Okay, so we can go ahead. So this finished training. So now we can run the rest. So here we prove that going back, we can see that the discriminator can tell from real versus fake. Okay, we load the generator class. Now we're going to generate our random image. There it is, random. We instantiate the GAN, the generator, and the discriminator, and now we start training it. So let's let it train. So this is going to be a long, long. Hopefully it'll finish. Okay. That's it. That's basically the whole process of training a GAN. And the tricky part, as I said, to understand is, I think this one is pretty obvious. You give it a real image to the discriminator, the label's a 1. You give it a fake image to the discriminator, the label is 0. What might be a little bit tricky to visualize is that for the generator, it uses the discriminator, right? But it's trying to fool it. And so the label that we give to it is a 1. Remember, the generator adjusts the weights, right? And it produces an image of a Picasso. And then the discriminator should say, if it says it's a 0, well, the label should be a 1. So what does that mean effectively? That the weights are bad. So you change the weights again of the generator. What does the generator do? It generates another Picasso. That Picasso goes into the discriminator. What does the discriminator say? That's a 0.5. Okay, it's closer to 1, but not exactly. So it adjusts the weights accordingly. The next time around, the generator generates a nice Picasso. It goes into the discriminator. What does the discriminator predict? A 0.9. Is that close to the 1 that you're providing? Yes. So what does that tell the neural network? This set of weights is the best one. Do you see how that works, guys? Questions on that idea? That's the key fundamental concept of the generator that It's a little bit difficult to visualize. Okay, so it's very slow, actually. Unfortunate. So hopefully you guys are following along. Maybe it's faster for you, but it's taking a while here. All right, so then after this, so we need to train it, right? Train the whole GAN. And then we can print the losses. For the discriminator and the generator. And after that, basically comes this code. So this is the code where we actually now give it a condition that we want, and it should render an image according to that condition. So the way this code works is very simple. You give it a label, whatever you want it to be, from 0 to 9. Then it's going to create the one hot encoded vector, right, of all zeros and a 1. Then this is just to create a plot that is 2 by 3. But if you notice, what's important is this part here. The generator is now trained, so you invoke g.forward. You generate a random vector of size 100, but instead of giving it a random thing, now you give it the vector of size 10 corresponding to the label that you want. Does that make sense? That's the key, guys. So we give it now the vector corresponding. So if we do this and we run G forward, then it's going to generate output. This output just gets reshaped into 28 by 28, and then we show it. Do you see that? Okay, so it's still running, unfortunately, and it'll take a while, but I can show you the output on the GitHub, and you can see that we want 9s, right? The condition is 9s. What do you guys think? Do those look like 9s to you? That's a conditional GAN. If it wasn't conditional, this would be a whole bunch of random numbers, right? But now these are 9s. So I did it for the 3, right? So if you notice here, same code, just change this to a 3. What do you think? Do those look like 3s? These numbers are generated. Okay, these are not from the data set. This is generative. So this is like, you know, it's a generative model generating 3s, for instance. We give it a 1. You can see the 1 there. What do you think? Do those look like 1s? They are 1s. And this is, once again, a conditional GAN. So this is, you know, stable diffusion obviously is way more complicated, but this is where you start to get to this, a rabbit with a hat and a spacesuit on the moon fighting Transformers, something like that, right? So that's where you get to that. You start with this, obviously, and then build it up accordingly. Here's a number 5. You read it in. Do those look like 5s? This is a pretty good 5, I think. I mean, it makes some mistakes, obviously. It's not perfect, but I mean, it's not a GPU. I don't have... Remember that stable diffusion was trained with probably all the images in the world, right? So those models are huge. And, you know, you can see how this GAN is very slow to train, actually, and it's only the MNIST data. 60,000 images. Oh, I have another one. 4. I think, oh, this is where I actually use the function. So I guess my function does work. I didn't think it worked, but I guess it does work. And then this, you give it a 4, and that, you know, this looks like a 4. This looks like a 4. Probably not that one, although sort of, right? And that's it. That's a conditional GAN. Any questions? This is the last topic of the semester, of the class. So, you know, we did basically classifier, we did regression and classification, right? With neural networks. Then we did CNNs. And then finally, we did 2 generative models, transformers, and generative GANs and conditional GANs. So it's still training. Yeah, it's still kind of slow, unfortunately, but we can go over here to the, if we go here to GANs in the repo. So this is CGANs, but I also did MNIST GANs. So it's almost the exact same code, but I just want to point out the little differences. So you can probably spot them, right? So do you see here the difference? 784. In the CGAN, this was, plus 10. Very good. Thank you. And then if we look at the GAN, do you see the difference? In the CGAN, this was plus 10. That's it. You see how simple that is? And then some tricks of generating random vectors in the training, like when we do the actual this, right? So we provide random seeds, etc. But we don't need conditions for this one, right? So we only needed conditions for our CGAN. Yeah, so anyway, that's basically it. At this point, I'm just waiting for it to train, but at this velocity, at this speed, yeah, it's not going to finish today. I leave it for you guys as an exercise. Have fun with this. Play with it at home. I would basically run this code from beginning to end, and then make sure that you can in fact get conditional values. Oh, going back to this one, this non-CGAN, if you notice, it just generates several numbers, right? So if you look, that's a 9, that's a 9, so it looks like a 2. Do you see that? So these are more like, because this is the not the CGAN, but just a regular GAN of MNIST. And if you look at it, this looks like a 3, a 2, a 2, a 9. But just by adding that conditional vector part, then now we can actually indicate right what we want. So we want a 9 or a 3 or a 1 and so on. Any questions, guys? Yeah, so unfortunately, as I said, I won't be able to, it's taking too long to train, but you can see the Jupyter, that would have been the same output, and I just leave it for you guys at home to try this out. All right, so I'm going to stop the recording now. Hopefully that recording worked.